right. Does that kind of make sense? No, still doesn't make sense. So if the statement is, if you give me $10, then I'll buy dinner. So under what circumstances can you accuse me of lying to you? The only time is if you do give me the $10, but I don't buy the dinner. If you don't give me the $10, then you can't accuse me of lying, regardless of whether I buy the dinner or I don't. So the only time when it can be false is if the first thing is true, but the second thing was false. Because it's if the first thing, then the second thing. So if the first thing never happens, then it's kind of, it's what they call like vacuously true. So it's just, it's only true because your premise was false, you know? So you can only, it's like you can't accuse someone of lying or of something like that if they're starting from a false premise. Because if this is true, then a bunch of other stuff. But if the first part wasn't true, then it kind of doesn't matter what the other stuff was. So anyway, that implication statement, so even if you can't understand it, you can at least memorize the fact that that type of statement is only false if the first part's true and the second part is false. All right. So then the biconditional, that's the double arrow. So in that case, that one is only true when they are the same. So in other words, if they're both true, it's true. And if they're both false, it's true. And then otherwise, if one is true and one's false, then the overall statement is false. All right. So those are kind of like the rules that you use. And then number one is an example of a problem that you might actually be given. So again, those first two columns are just going to be the same. And on the test, I would just fill those in for you. So it's just all the possible combinations of trues and falses. All right, so then the next column is not P. So not P is just the opposite of whatever it says in the P column. So the P column is TTFF. So this is going to be FFTT. And then the next column is Q and not P. All right, so in this case, we are focusing on the Q column and the not P column. All right, and okay, so it says and. So the and statement is only true when they're both true. So that would be false, false, true, false. Right, those two that I highlighted, because it's Q and not P. So you just want to look at those two columns of Q and not P to answer the last column. It's like what? Well, it's the Q and it's the opposite of P. Mm-hmm. All right, so number 2 has 3 statements. It has P, Q, and R. So this will require 8 lines on the table. And again, so those first 3 columns, it's just going to be all the possible combinations of trues and falses for 3 statements. Again, don't worry too much about figuring out what to put there, because in the terms of the test, I will fill that in for you. But basically what I'm going to do is for P, I'm going to have 4 T's and then 4 F's. And then for Q, it's going to start with, it's going to be 2 T's, 2 F's, 2 T's, 2 F's. And then for R, it's going to be every other one, T, F, T, F, T, F. So that's just a quick systematic way of writing down all the possible combinations of T's and F's there. Okay, so then for not Q, so that's the opposite of the Q column. So the Q column is TT, FF, TT, FF. So for not Q, it's going to be FF, TT, FF, TT. All right, so then next we're looking at not Q or P. Not Q or P. So we're looking at the not Q column, and we're also focusing on the P column. Those are the 2 columns that we're focusing on for the next thing. So it's an OR. So OR is only false when they are both false. So otherwise it's true. So I know it's only false when they're both false. So let me find the falses here. So here's one and here's one. And then all the rest of them are going to be true. Okay. And then the last column, we have R, if R, then not Q or P. All right, so let's see. All right, so we're looking at the R column is one of them that we're looking at. And then the other column we're looking at is that one. So those are the 2 columns we're going to focus on right now. All right, so now the statement with the arrow, so it's only false if the first one's true and the second one's false. So let me see if I can find any. So there's one right there where it's false. The first one's true and the second one's false. All the rest of these are going to be true. All right, number 3. Okay, so just have P and Q on this one. So T, T, F, F, and And then TF. All right, let's see. So on this one, you'll probably see some like this on your homework, but I probably won't put one exactly like this on your test, in that the part that's different is like they're wanting you to figure out what needs to go in here. Okay. So as far as that part goes, I probably wouldn't put that on your test because it'd just be too annoying to grade, but you'll see that on your homework. Okay, the columns that we need to have a column for not Q, we need to have a column for not P, and then we need to have a column for not Q and not P. So basically just breaking it down in parts. Right. So then not Q, so that'll be FT. And then for not P, that'll be FFTT. All right, and then let's just focus on those two columns to answer the next column, which is not Q and not P. All right, so that's an and statement. So in order for the and statement to be true, both of the statements have to be true. So that'll be this one here at the bottom, and then the rest of them are all false. All right, and then the last column is a double arrow, or in other words, the biconditional. So on one side of that double arrow, you have the P column, and then on the other side of the double arrow, you have this and column right here. So those two blue columns that I just highlighted, that's what we're going to look at to answer the final column. Okay, so in order for the double arrow statement to be true, those two columns have to have the same truth value. So either both trues are true or both falses. That makes it true as well. So we only have one true then, which would be this one right here, where they're both false. And then the others are false. Okay. Number 4 says determine the truth value using truth tables. All right, so we have a statement here. Obama is the president if and only if 1 + 1 = 2 or 3 + 2 does not equal 6. My little not equal to symbol is messed up. It's supposed to be a equals with like a slash through it. Okay, so I'm going to break this down and say, okay, so the statement Obama is president, that would be P. And then we have another statement which says 1 + 1 = 2, so I'll call that Q. And then our third statement is going to be R, 3 + 2 = 6. So statement, okay, so we have P is false, Q is true, R is false. So the whole entire statement overall is P with a double arrow, if and only if Q, so that's going to be parentheses, Q or not R. Okay. All right, so that's the whole statement. So then let me write down a column, and we don't need to fill out all the possible trues and falses, because in this case we know what the statements are and we know whether they're true or they're false. So then let's put a column for not R. So since R is false, that means not R is true. And then let's do a column for Q or not R. Well, yeah, something similar to that. I think it's over a week away. Let's see. For chapter 3, yeah. This is pretty much the end of chapter 3. Yeah. So we have still, yeah, a week and a half until the test. I know it's weird. It takes some time for it to sink in, some practice. Okay. Let's see. All right, so Q or not R. So if we look at Q, not R, so the or statement would only be false if they were both false. In this case, they're both true, so the or statement is true. And then at the end, the double arrow, the biconditional statement, that is true whenever both sides of it are true, or both sides of it are the same. So we have one side of it is P, one side of it is this or statement. One's false, one's true, and so therefore this is going to be false. So ultimately the answer to this is that the overall statement is false. Maybe you can, I don't know, but it's kind of like one of those things, like if you have a algebra equation, you know, can you just look at it and be like, oh, x is equal to 2? So like the other, yeah, I mean, I just put like a random amount of columns on there. Yeah. Just use however many you actually needed.
So going to be true. We obviously know 2 plus 2 doesn't equal 6, so that can still be true though, regardless, like on there, on 2.
You mean like the overall answer could still be true?
I'm asking, like, because like,
so
not like in this situation, but like if we was like worded different and everything.
Yeah. So
like,
if I said, okay, so for example, instead of saying Obama is the president, if I said Trump is the president, then the overall statement would end up being true.
Really?
Yeah. So the only reason why the statement ended up being false, because the overall statement is an if and only if statement. Okay, so the if and only if statement is true if both sides are the same. So if both sides are both true or both sides are both false. So like if I would have said, you know, Trump is the president, that would be true. And then the other thing was also true. So yeah, I mean, so 3 + 2 doesn't equal 6, but in the actual statement, it says 3 + 2 does not equal 6, you know, which is true. So yeah.
Is that what one like a slash between this one?
Yeah. 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 So it's what it's saying is it's saying 3 + 2 is not equal to 6.
That makes it right.
So that makes it true. Yeah. All right. All right. I'm going to go ahead and start on chapter 2.
Sorry, Dylan, we're moving on this.
So we're done with going over chapter 3, and we're going to move on to chapter 2. Chapter 2 is kind of related. You may not realize that at first, but it have some similarities. So yeah, so we'll finish chapter 2 this week, and then next week we can, like on Tuesday, we can review everything from both these chapters.
Well, is our test going to be over both of the chapters?
Yeah, it's going to be over chapters 2 and 3.
I was going to say, we're going to forget this.
Yeah, we can, like I said, it's all kind of sort of related. So we'll finish it up this week, and then next week on Tuesday we can review before our test on Thursday.
Did you already grade the test?
Almost. I'll finish them up today for sure. All right, so chapter 2 is about set theory. So a set is a collection of distinct or different things. Those things are called elements of the sets. Okay, so here's a couple examples of sets. So a set can just be like a list of a few things. And we put those curly braces around it, kind of shows that it's a set. So set A has the elements 1, 3, and 10, and then set B has the elements N, X, 0, 10, 23, just for some examples. So here's some of the symbols that we use in this chapter. So here's a symbol for is an element of, and then a symbol for is not an element of. Basically the same one. So it kind of looks like an E-ish. And then a slash through it for not an element of. The empty set is a set that has no elements. So most of the time that is symbolized by like a circle with a slash through it, but it could also be symbolized by just two of the curly braces with nothing in between them. Then we have the set of natural numbers. So I think when you see this on your homework, it just kind of looks like a bolded N. But when I write it, the way I learned it was like a N with like these two sticks going across. So that's how I like to write it. So that's the set of natural numbers, which starts at 1, and then it's just everything that counts up from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know, up to, you know, 1,000,000 and beyond. Okay. So number 1 says, describe the following set. Okay, so I could describe that by saying that is the set of natural numbers that are greater than or equal to 10. That would be one way to describe it using words. Oops. All right. And so next it says write the set as described using the roster method. So the roster method just means you're listing the elements. So all the letters in the word carry. All right, so I'm going to use curly braces, and the order of the elements doesn't matter. And you only list each element one time. So even though the word carry has 2 R's in it, I'm still only going to list the R one time. So a lot of times we like to list them in alphabetical order, but it's not really necessary. I mean, in that case, I just listed them in the order that they appeared in that word. So that's fine too. Okay. All natural numbers less than 4. Okay, so they want me to write that using the roster method, so listing them. So natural numbers less than 4. So that would be 1, 2, 3. And the way they wrote it right here, this is called set builder notation. And it's saying basically all values of x such that x is an element of the natural numbers and x is less than 4. And they'll ask us to use that also here in a second. So number 4 is saying all values of x such that x is an element of natural numbers and x is greater than or equal to 7. So to do that using the roster method, so it's greater than or equal to 7. So it starts at 7 and then it just keeps going from there. And so I can list a few and then just say dot, dot, dot. Okay, number 5, x such that x is a month that starts with J. So January, June, July. Number 6, all values of x such that x is an element of the natural numbers and x is less than 1. So what elements would be in that set? Yes. Because there are no natural numbers that are less than 1. So that would be equal to the empty set. Okay. So A is the set of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. All right, so let's answer true or false for the following problems. So number 7 says 2 is an element of A. Is that true or false? That's true. Number 8 says 10 is an element of A. Is that true or false? That's true. So even though it wasn't specifically listed, we can understand from the pattern and the ... in the middle that that also includes 8, 10, 12, 14, 16, 18 as well. Number 9 says 12 is not an element of A. That's false. What about number 10? That's actually false, because what it says is the set containing the element 4 and 6 is an element of A. So it seems like a fine distinction, but the elements of A are just the individual numbers. So there is no, so a set is not an element of A. So that in the next section, we're going to cover subsets. So it would be accurate to say that that set of 4 and 6 is a subset of A, because 4 and 6 are elements of A, but that whole set itself is not an element, because only 4, you could say 4 is an element, you could say 6 is an element, but you can't say that set is an element. Because it's not, because the elements of A are numbers, the elements of A are not other sets. So there's a difference between the number 4 versus a set containing the number 4. Those are two different things. So 4 could be an element, but the set that contains the number 4 is not an element.
So you're saying 10 is not a set?
10 is not a set, 10 is just a number.
What is in those things that you put on the set?
10 right here. Okay, 4 and 6. Oh, I'm sorry. 4 and 6. Okay, so that is a set containing 4 and 6.
So what would make it true?
Well, one thing that could make it true, so like if I said 4 is an element of A, that would be true. If I said 6 is an element of A, that would be true. But if I said a set containing 4 is an element of A, that would still be false, because that's a set, not a number. There's a difference between a set that contains a number, and then just the number by itself. Like I said, there is a concept that we'll learn more about in the next section called subsets. So it would be true to say that instead of saying it's an element of, if I said is a subset of, that would be true. That would be true. It is a subset, so that's what we call a subset, but it's not an element. So it's just an issue of terminology. So the cardinal number of a set is the number of elements in the set. So in this case, the set A of A, so the number of elements of A would be 12. I always forget, I need to add another example right here. Let's say we have a set called B, and let's say that it has, let's see, 12, 15, 18, and then let's say 300, 303, 306. Okay. All right, and let's say we wanted to evaluate the number of things in B. So sometimes, so N of B, so the cardinal number, it's the number of elements. So sometimes the number of elements is completely obvious. You just look at it and you just count the elements and that's it. All right, so if that's the case, great. Like for example, you know, those two little examples I gave at the beginning of this chapter, look at those real quick. So for that set A right there, 1, 3, and 10. So the cardinal number of that set would be 3, right? For this set B right here, 1, 2, 3, 4, 5. The cardinal number of that set would be 5. So if you can just look at it and you can know what the number of elements is just by, you know, quickly counting them or whatever, then easy peasy. But a more complicated thing can happen like this. Okay, and I'll show you how to calculate it in this case. So in this case, we have, all right, we're gonna do 306 minus 12 divided by 3. And I'm dividing it by 3 because it's counting by threes, right? Like 12 plus 3 is 15, plus 3 is 18, so on and so forth, up to 300, plus 3 is 303, plus another 3 is 306. So see, it's counting by threes. Okay, and then finally, I'm going to add 1, and I'm always just going to add 1 at the end because think about when I did 306 minus 12, I took the 12 away, but the 12 is there, so I need to add 1 more back in. So if I calculate that, that's going to give me the answer. So 306 minus 12 divided by 3, and that's 98. So add 1, that'd be 99. Okay. All right, so there's that method that you can use. So if you need to use that, if it's a set that has a lot of elements in it like that, then do that. But every time it asks you for the cardinal number doesn't mean you have to use that method, okay? A lot of times you can just look at it and it's just obvious. Like, for example, if I said set C has elements 6 and 50. Well, how many elements are in that set? 2. Done. No formula needed. You just look at it. It's obvious. Okay. All right, so the concept of equivalent sets and equal sets. So equivalent, two sets are going to be equivalent if they have the same number of elements. They are equal if those elements are the exact same elements. All right. So the order of the elements doesn't matter, and then repeated elements don't count. So I would cross out any repeated elements. All right, so both of these sets have 3 elements. So that means they're equivalent. And those elements are the same exact elements, 1, 2, and 3. The order doesn't matter. So they are equal. Number 13. So the cardinal number for each set, they both have 3 elements. So they are equivalent, but the elements are not the same elements. One is 6, 7, 8, the other one is 7, 8, 9. So they're not equal, but they are equivalent. Okay, number 14, set A has 3, 4, and 5. Set B, let's write that out in roster method. So that is, so natural numbers between 3 and 6. So 3 is included because it says 3 is less than or equal to X. So it does start at 3, and then 4, and then 5. And then 6 would not be included because it says X is less than 6. So it's just 3, 4, and 5. So they both have 3 elements, which makes them equivalent. And those 3 elements are exactly the same, which makes them equal. Okay. Finite versus infinite. All right, so hopefully you have sort of a understanding of finite versus infinite already.
What is finite?
Well, finite, it's like not infinite. So so as far as in terms of a set, if the set has a cardinal number that's equal to 0, meaning it's the empty set, or if the cardinal number is a natural number. Okay, so the set of all living humans, would that be finite or infinite? That would be finite. So there is, you may not actually know what the number is, but there is a, you know, assuming if you believe in God, God probably would know what that number is, right? I mean, the number exists. There is a certain number of humans, you know, it might be 6 billion and something, right? But it's not infinite. All right. So number 16, x is all values of x where x is a natural number and x is greater than 500. So would that be finite or infinite?
Oh, greater than 500?
Greater than 500. So that's infinite because there's no stopping point. It would just keep on going up forever and ever. And then number 17, all values of x such that x is a natural number and x is between 1 and 2000. So that would be finite because it's got a starting point, it's got an ending point. You know, we could calculate the cardinal number of that set. Okay. So write the following sets using set builder notation. So all those times when it says, like on number 17, for example, that's set builder notation. That's what they're looking for. So number 18, we have 5, 6, 7, 8, and so on. So to write that in set builder notation, that would be values of x such that x is an element of the natural numbers and x is greater than or equal to 5. Right, number 19, you can say x such that x is an element of the natural numbers, and we can say x is less than or equal to 87. So it's not necessary to say like from 1 to 87 because natural numbers already just go down to 1. Number 20, that's going to be all values of x such that x is an element of the natural numbers and it's between 10 and 102. So we can say 10 is less than or equal to x, which is less than or equal to 102. And then for number 21, we have A, E, I, O, and U. So we could say all values of x such that x is a vowel. All right. that is the end for today. End of 2.1, and then we'll do 2.2 and 2.3 on Thursday. I promise I will have your test grades in today, probably within the next couple hours.
Do they go on? Website?
Canvas. Mhm.
Do we have a canvas right now?
Probably not yet.
I just thought it was new on the test.
Since I'm not actually finished, it's kind of hard to say.